Okay, in this video we're going to look at how we can experimentally verify Boyle's law, or essentially what that means is prove that Boyle's law works. So let's have a look at the equipment we would use to do that. So the equipment I would use we've got here. So what we've got is some fixed masses which we're going to use to apply a force to a syringe. We've got a sealed syringe here, so it's had its ends melted together, so we've got a fixed a number of moles of gas. We've got it G-clamped to the table, so we can ensure that this apparatus doesn't topple over and we can be as safe as possible. We've got a thermometer to monitor the temperature of the surroundings. We've got a micrometer that will allow us to measure the diameter, which will allow us to work out the cross-sectional area of the syringe. And lastly, we've got this wooden block on the top of the syringe that just allows us to apply bigger loads to it. As you can see, we've managed to balance a load on the top there, and it also has a string attached to it so we can hang even more masses off it, so we can apply a nice big load to our setup. Okay, so that's our equipment. So first off, some general things about how this is going to work. So before we even hang any masses on there, there's a volume of gas inside the syringe, and it's at a stable or equilibrium position. And the reason for that is because the pressure inside the syringe is equal to the pressure outside the syringe. So there's no resultant force to make the syringe plunger move up or down. So when we hang these masses on the syringe, what we're going to do is we apply an additional load. So we've got atmospheric pressure, and we add onto that some extra pressure from this additional load. And at that point, there'll be a greater pressure on the pushing down on the syringe than there is from the inside pushing out. So there'll be a resultant force that causes the plunger to move down and decrease the volume of gas. So when you decrease the volume of gas, the pressure is going to rise, and you'll reach a certain volume where the external pressure is equal to the internal pressure, and will reach a new equilibrium position. So at that point, essentially the pressure from the outside and the pressure from the inside will again be equal to each other, and we can then figure out what the internal pressure is using atmospheric pressure and the pressure from the load. That's the general setup we're going to use. First thing, or one of the first things we need to do is we need to use a micrometer to measure the diameter of our syringe, because then it'll allow us to calculate the cross-sectional area. Because what we want to do is figure out how much pressure the load or the masses we're applying create. So if we take the weight force of the masses divided by the cross-sectional area, that will allow us to figure out what the load pressure is, as I've called it. And I wouldn't just measure the diameter in one place, I'd measure it in several different locations, and we'd calculate an average diameter for the syringe there. Okay, so that's how we figure out what the load pressure is. So in terms of doing this experiment, the first thing people often do is that they will plot a graph of pressure against volume. They'll see that as pressure increases, volume decreases, and go, we've verified Boyle's law, whoop-de-doo, we go us. Is that right? No, that is just plain wrong. This graph does not show pressure is inversely proportional to volume, which is what Boyle's law says. The reason for that is this graph doesn't tell you anything about the kind of relationship between pressure and volume. This could be an inversely proportional, it could be like an inverse square, an inverse quad kind of graph. This doesn't tell us a precise relationship at all. So what graph do we need to plot? So one option is to plot pressure against 1 over volume. So if pressure is inversely proportional to volume, this graph should be a straight line passing through the origin. So inversely proportional and directly proportional to 1 over are the same thing. We could have also done a 1 over pressure versus volume graph. That would have worked. Because the cross-sectional area of our syringe is a fixed value, we could have done load against 1 over volume. We could have done mass against 1 over volume. All of those would have given us evidence that Boyle's law is working. But this is the graph it's easiest to see it. We've got pressure against 1 over volume, so that's what I've gone for there. An alternative thing we could have done is use logarithms. Up on the top left, you can see a general equation linking pressure and volume. So what we say is we think pressure is some sort of function of volume, but we don't know what power volume is raised, and we don't know what volume is multiplied by in the equation. So what I'm going to do is take the logarithm of both sides and then apply some of the log rules you will learn about in maths to turn it into the equation log P is equal to log K plus A log V. So if we plot log of pressure against the log of volume, you can see that A will be the gradient of that graph and then K will be the y-intercept there. So if we go back to Boyle's law, so Boyle's law states that PV equals K at a fixed temperature, or we can write that as P is equal to K times 1 over V. So if we compare that to the general equation at the top, we can see that A should be equal to -1 if Boyle's law is correct, and that the ln K value should give us the constant in the equation as well. So this would be another way of experimentally verifying Boyle's law if we get a gradient of -1. So those are the two ways we could use. So let's have a look at our control variables. So with any experiment, there's always going to be some things we need to keep fixed during the experiment. And because we're using Boyle's law, that tells us we need to be making sure temperature is constant during our experiment. So we can't really, in a general classroom setting, keep temperature the same. It's just not something we can control. But what we can do is monitor it during our experiment to check that it doesn't vary greatly. And if it does change enough, we can stop taking measurements and actually we would chuck that data in the bin and start again because we haven't had a controlled temperature. Just a side note here, in some scenarios you'll use a water bath as a mechanism to control temperature. Sometimes when you're dealing with experiments where you're trying to change the temperature and investigate something else, you can use a water bath, but that just would not be appropriate here. We can't be hanging masses inside a water bath. That just doesn't make sense. So you might have thought of that. It's not a bad idea, but it just doesn't make sense for this practical to control temperature. So another thing we're keeping the same is the cross-sectional area of our syringe. You'll notice it's cylindrical in shape. And the reason we're doing that is we want to be able to calculate the pressure regardless of where the plunger is in the tube. So we're keeping the cross-section area the same. That's a nice, easy calculation. We're also using atmospheric pressure as part of our calculations. So realistically, we should have some mechanism to measure it for each of the different readings. So we can get load pressure and atmospheric pressure together. Like I said earlier, we've melted the end of the syringe together, so it's completely sealed. And what that means is the number of moles of gas has stayed constant. And putting all of those things together, if we've got the ideal gas equation here, we've got a strategy to control N, R is a constant, we've got a strategy to monitor T, so we can see that pressure and volume are the only two things changing, and we've got an effective experiment to investigate their relationship. Okay, so that's our setup. So let's have a look at actually practically doing this. So the first thing I measured was the diameter, and I measured it in 3 different places and got 3 different values. And I calculated an average to use to calculate the area. So that's what I've done here. And I've measured the diameter, got average, used pi d squared over 4, and I've got a cross-sectional area there, which I've kept as an unrounded value because I'm just going to be using it in calculations. You'll notice I've converted it already into meters squared. I want everything in SI units to be using later on. The other thing you might have spotted at this point is that the resolution of our syringe is actually very large. It actually has 1 milliliter divisions, I think it was. So what we're going to do is, to get slightly better data, we're going to estimate what the next decimal place is. So you can see it looks like it's about 10 milliliters. We averaged the next decimal place and said it was either 10.1, 10.2, that sort of thing. And the reason we're doing that is because we just don't have large enough masses to cause big volume changes. So we need some way of getting more readings with smaller masses. So we're going to have to estimate. It is a source of uncertainty, but not a significant one. So it's okay to do that. So if you have a look at the table of data you'd collect, You can see I've got all the masses down here, all of them to 3 decimal places, because we've got fixed masses of like 100 grams or 200 grams, so we know them to the nearest gram. You'll notice all the volume measurements have an extra decimal place than you'd expect, but as I just explained to you, we've estimated those by looking at the syringe and going, oh, you know, this is about halfway between divisions, or it's about a quarter of the way through divisions, that kind of thing. So that's what's allowed us to get this extra decimal place, which would normally not be appropriate. And you can see we've got column headings with units, and where I've got powers of 10, you can see those in the column headings as well. So we keep all of that stuff out of our table. So in terms of why we've got different numbers of decimal places in the pressure and the volume to the -1 columns, the added pressure we've calculated using mass, we've calculated using 9.81, and we've calculated using cross-sectional area. So we have to give these all to 3 significant figures because G with 9.81 is a 3 significant figure number. So that's why we've got different numbers of decimal places in that column. They're all 3 significant figure numbers, likewise for total pressure. And the same for the volume. You can see in the top row, we've kept 3 significant figures because we've just taken the reciprocal of a 3 significant figure number. The other ones are all 2 because we've taken reciprocals of 2 significant figure numbers. So that's why those columns are a bit different. And it's because those values have been calculated, not because they've been measured. So when you measure data, you should record it to the instrument resolution. When you calculate data, you need to keep consistent significant figures there. That's what's going on. Okay, so let's have a look at the graphs we would get. So using the pressure against 1/volume graph, we get something that looks like this. So the first problem that you might notice here is this graph doesn't extend back to the origin, because to plot our data using as much of the graph table as possible, I haven't used 0, 0 as the origin, I've used a different number. So what I've had to do is use a least squares regression method to calculate the equation of this line, which we can see is y equals 101x. So there's no y-intercept there, so that tells us this graph goes through the origin. We can see it's a straight line, so it's a straight line passing through the origin, so this confirms Boyle's law, or it verifies Boyle's law there. So we need both of those things. It's not enough that it's a straight line. It's a straight line through the origin, and sometimes we have to calculate what the origin is, or the y-intercept is. So in this case, this graph verifies Boyle's law. Have a look at the log graph. I use log to the base 10, though it doesn't matter. Again, I've plotted the data, use a least squares regression method to work out what the equation is. And this time we don't really care what the y-intercept is, but we can see the gradient is -1, again verifying Boyle's law. So just the thing to flag up at this point, you'll see that there are no units on either of the axes. That's because when you take the logarithm of something, it becomes unitless. So that's why we've got no units, whereas you'd always expect to see a unit of something on the axes on a graph. Okay, so those are your different methods for verifying Boyle's law. I hope you found that useful. If you have any questions you'd like to ask about anything in this video, please feel free to do so in the comment section. I'd be more than happy to answer for you. But thank you very much for taking the time to watch.